Okay, hello and welcome everybody to my talk, You Have Become the Very Thing You Swore to Destroy, Remotely Exploiting an Antivirus Engine. My name is Simon, I'm a cloud vulnerability researcher at Google, so I'm usually not very deep into reverse engineering, so I'm even happier I was invited here to give a talk. So let's just get right into it. The antivirus engine we're going to target today is called ClamAV. It's an open source AV engine for Linux, macOS, and Windows, but it's particularly popular for Linux. And it's widely used in server-side context. So email servers will have it run in the backend and will scan each of the incoming emails and outgoing emails for viruses just to make sure everything is clean. There are also some email suites like Zimbra where it comes installed by default. Then, according to Cisco's advisory, their appliance, Cisco Secure Web Appliance, was also affected, which means if you could pawn it, you effectively control the organization's network traffic. And then it's also somewhere in the backend of customized cloud storage pipelines. The user somewhere uploads a document, and before it's finally stored, it's going to be scanned. And it is written in C, so you can already guess that we're going to exploit some memory corruption issues today. Achieving remote code execution in ClamAV would give an attacker privileged access to highly sensitive data, such as emails and up and downloaded files. Let's just do a very high-level overview into how it works, just so we're all on the same page. It supports file type detection and recursive scanning of many file formats. So if you give ClamAV a file, it will try to detect what kind of file it is. And if it's something like an archive or a container file, it will unpack it and then recursively scan these files. And the recursive depth and number of files are just a configuration setting. So this diagram is basically the exact same thing. In the beginning, we detect a file type, and then afterwards, a giant switch statement is executed where it says, hey, if this is a raw archive, unpack it and call this function again. If it's a file like a PE or ELF file, it will try to actually detect the virus, and then we have this recursive loop. I won't go into much detail how they detect viruses, because that's not really part of the exploit strategy today. But they have all sorts of options, from simple hash matching to bytecode plugins. So what's the threat model here? Let's say as an external or internal attacker, you can somehow get a target ClamAV instance to scan your files. So in this case, you would, for example, you could upload files via web form, and before they're uploaded somewhere, they're scanned, or you send an email to someone's server, and before the email arrives in the mailbox, it's scanned as well. And then the attacker would discover vulnerabilities in one of the parser for one of the many file formats that are supported. Some of them are quite complex, like HFS Plus or CPIO or DMG. And then once you found a vulnerability as an attacker, you would try to get the ClamAV instance to just to parse this file and then trigger the vulnerability. And this can be quite easily achieved because due to the nesting property of ClamAV, say you have a web form that only accepts zip files, you could just place your file into that zip file. And so your attack surface is quite large in default configurations. So the agenda for today is we'll look at why the usual approaches to defeating ASLR and InfoLeaks won't really work with ClamAV and why that's an interesting target. And then we'll go a little bit into the bugs we found. Won't go into very much detail because the bugs are pretty standard. However, the exploitation strategy is very interesting, and we will see why. And then lastly, we'll do a real-world case study of an authenticated RCE on an email server. So why do common InfoLeak approaches don't really work for ClamAV? So let's just assume an environment. In this environment, full ASLR is applied to loaded libraries and files. An attacker gets to see the scan result. So let's say they upload a file on a web form, and then the web application in the backend scans ClamAV and tells them, no, there was a virus detected. You can't, there was an error. Or no error. And then we also assume the upstream ClamD multi-threaded server mode, which just runs with multiple threads, which means if you cause a seg fault, the entire thing is gone and it will need to restart. So usually what happens, roughly, when you exploit memory corruptions remotely, is you have a multi-stage approach. So in the beginning, an attacker would try to cause some sort of InfoLeak, would exploit an InfoLeak vulnerability. So they establish some sort of protocol connection, whether that be HTTP or a custom protocol. And then if everything goes right, the target would reply with a pointer in the response. So somewhere in the response, we have a pointer, and from there, we can derive the location of libraries in memory, and so forth. And then with this information, the attacker can now craft another payload and craft a rob chain that will exploit another vulnerability or the same vulnerability. And if the attacker gets lucky, the target responds with a reverse shell. Now, this doesn't apply to ClamAV. And the reason is that ClamAV is a non-interactive target. So you don't really have a protocol exchange with it. And at the very most, an attacker can see if the scan resulted in a virus or not. And even then, in most environments, realistically, you're not talking directly to ClamAV. There's some sort of intermediary server, like a web application, that scans on your behalf, and it will display a custom error message to you. So there's no real way to get ClamAV to send you a pointer. Just to illustrate this again, we send the infoleak trigger, which is contained in a file, to web application. That sends it to ClamD, and then ClamD only replies with virus found or no virus found, and then the user or attacker receives some sort of error string. So we have this issue now with ASLR, where an infoleak becomes very difficult. So some of the alternative approaches we considered but didn't follow was going for a partial pointer overwrite, where you only overwrite a couple of bytes for a pointer, and then if you're lucky, you could call a function like system, and then execute a shell command. But we didn't really find a gadget for this, at least none that would have been acceptably reliable. And then, so we didn't really follow this path. And then data-only exploits could work, where instead of trying to get a rob chain, you would try to corrupt some data on the heap that leads to RCE. For example, ClamAV dumps the files it scans to disk with a randomized path before it scans them. So, for example, we could try to overwrite the randomized path where files are supposed to go on the heap, and then gain an arbitrary file write primitive with this. But the problem is this: the ClamAV user isn't very privileged on the system, and if the AV engine is sandboxed, this won't work at all. But this is still research that can be done. For example, when the target environment is known and you know where you would have to place a file, for example, a PHP file or a jar file, to get code execution, this could work. And then the last option is just a naive ASLR brute force. But this won't work because ClamD runs in multi-threaded server mode, which means it would have to restart after every segfault, which can take a long time because it has to load signatures, maybe even download signatures, and so forth. So let's get into the bugs, and then we can see how we can exploit ClamAV with all of these constraints in place. So the first bug is a heap buffer overflow. It was in February of 2023. Cisco released an advisory on it. It is tracked as CVE 2023 232, has a CVS score of 9.8. And it's due to a missing bounce check. It's really just a mem copy buffer overflow, and it occurs while parsing HFS+, which is a file system by Apple. And this can be triggered remotely by an unauthenticated attacker in default configurations of ClamAV. So here we see the corresponding code, not all of it, but I don't want to go into too much detail. We can see that the read size variable is initialized by the volume header and its block size. And this value is essentially arbitrarily attacker controlled. And then in the next step, ClamAV tries to read size into the buffer from the file. And there is no check that read size isn't smaller or equal to buffer. So this is a fairly straightforward heap buffer overflow. It is a quite powerful primitive because the overflow size can be controlled, but it must be in a range of 4 kilobyte to 2 megabyte. And the overflow contents can be controlled as well, so you don't have any restrictions like no bytes can be included. And it can be triggered repeatedly in a loop. And we'll get to this bug later again. But from now I want to focus on the out-of-bounds read. So we reported an out-of-bounds read in roughly the same time frame to the maintainers of libmspack, which is an open source library to scan Microsoft cabinet files, which are archives used by Microsoft. And ClamAV uses this library to parse some of these archives. The out-of-bounds read is tracked as CVE 2023 29077. And it can be triggered in default configurations as well, and it occurs due to an integer truncation, as we'll see. So I just want to give a quick background on the CHM file format. I'll try to stay very high level, but it is quite important for the exploit technique. So CHM are Microsoft compiled HTML help files. And they're basically just archives that contain compressed and uncompressed files, namely HTML help files. And the archive consists of a file header in which you have some standard information like a magic number or the block size, things like this. And then you just have a variable sized array of file headers. So far this is fairly standard. And then you have some system files. These are just, instead of having headers, they store some of the metadata about the compression algorithm as a file, which is kind of interesting. These just have predefined names. And then finally, we just have the content files, which contain the actual help content. And again, ClamAV uses libmxpack to extract these files. So if we look at this, this is just the layout, fairly standard, a little bit simplified. And let's say we want to uncompress or extract an uncompressed file. Internally, libmspack builds a linked list. We can see this from here, from the next header. It just builds a linked list of the file headers, and then whenever it wants to extract the archive, just reverses the linked list, and then it goes on and on. And then we have one entry here called the section, and this basically just describes if the file is in the uncompressed data section or the compressed data section. And when the file is uncompressed, it's fairly straightforward. We simply read the offset and then seek to it within the uncompressed data section, then read length bytes, store the bytes in a buffer in memory, and then the caller can do with these bytes however they please. So this gets a bit more complicated when a compressed file needs to be read. So in this file, the file offset that was in the file header is not used as an offset into the file directly, but there is one level of indirection. So libmspack reads a system file called the reset table from the attacker supplied file into memory, and it's basically an array, and the offset of the file header is used as an index into the array, and the resulting value is used as the real offset. Now I want to say that the real logic is a bit more complicated, and there's a good reason for this indirection, and it's related to the compression algorithm. But I don't want to get too much into it because it's not very relevant to the talk or the exploit, and it would make everything more complicated. And the reset table file is just an uncompressed file with a special file name, which you can see here. I'm not going to read it out loud, but it just reverses the linked list and looks for that. So let's go back to our little visualization here. When a compressed file is encountered, we read the reset table file, and then we read the corresponding file header, and then let's say the offset was 0, which means we use index 0 to look up into the array, and then finally we seek to the real offset within the file. So libmspack treats the reset table file like a regular uncompressed file, which means it will allocate length bytes of memory according to the file entry, and then try to read the file into this buffer. However, it truncates the length field from 8 bytes to 4 bytes before it does this. So we can see this here in the code, file length, which is an arbitrary attacker value. It's unchecked. There's no real checks on it. It just relies on the fact that if this was an absurdly large file, it would just fail the allocation. So that's kind of the only check that was done on it. But here it is truncated to a 4-byte integer. So let's say we set this value to 1337, but we set the 33rd bit, which would result in a very large value. This would be truncated into 1337 again, because this extra bit that was set is truncated away, which means the resulting reset table buffer is 1337 bytes large. So the problem with this is that when the bounce check is made to look up from the offset into the reset table array, the untruncated value is used. So we have a difference here, and that's why we can read beyond the index 1337. So let's say we have position, set it to deadbeef, and then we set the reset table length to the enormously large value that we showed as an example earlier, but the data buffer is just 1337 bytes large. And then when position is here compared to the length of the file, this check would pass in this case, and when the buffer or the array is indexed, we have an out-of-bounds read. So this is the out-of-bounds read primitive. And it's pretty strong because the size of the reset table buffer can be arbitrarily controlled, which means it's pretty good for heap feng shui and getting a advantageous heap layout. And the out-of-bounds read size can also be partially controlled. We can decide between 4 and 8 bytes that are being read, and the out-of-bound index can be controlled on a byte basis. So it's very strong. And what's important for the rest of this talk is how the value is used that is read out of bounds. So in this case, it's trying to get the array, trying to get the real offset within the file from this array, but because it's out of bounds, this could be any value in memory. So let's see how we can plan ClamAV with these primitives. So we go back again to our visualization of CHM, and we make a couple of assumptions. So let's say we have a known virus that is embedded and compressed within the file. In order for ClamAV to find this file, the CHM file would have to be well formed, and it would have to be able to correctly seek to this file so that it can decompress it. So let's look at the code that reads the reset table initially for this entry, and this is where the out-of-bounds read occurs. The value that is finally read out of bounds is stored in the offset variable. And then there is some additional calculation done, which we can see here. And these two values, so offset, would, for example, contain a function pointer or a partial function pointer because it's read out of bounds. But these two offsets are fully attacker controlled. They're both 8-byte values. And the result of this addition is then stored in the in-offset variable. And then a little bit later, when it's time to seek to the offset data, we just seek to in-offset. So let's assume we can make ClamAV or a remote ClamAV instance scan our files multiple times or in an infinite amount of times. And we assume that we have a very reliable heap groom or a way to prepare the heap so that the out-of-bounds read always reads the same function pointer in memory. And the only thing we change for each of the scans is the values that are added to the offset, that are added to the function pointer that is read out of bounds. So if we do this, there is 3 places we can seek to, because the result of this addition will be random because ASLR is random. So the 3 places we can seek to would be somewhere outside of the CHM archive. This would be a wild value. We have no idea. In this case, libmspec would just return error, nothing would crash, and the virus isn't found. Now, the second possibility is that we seek somewhere, anywhere within the file. In that case, garbage is decompressed, or the decompressor just returns an error and says, I can't decompress this. And there is a very, very, very low probability that we seek exactly to the beginning of the known virus. In this case, the virus would be detected. So just say we just scan multiple times, only change the offsets, we seek here, here, here. Suddenly, we seek to the beginning of the known virus. And then that means the virus is detected and the signal is sent back to the attacker. So again, if we increase the offset, at some point the offset addition will result at the exact offset for the known virus, which means we can derive the value of the function pointer from here. Because it's a simple addition, we can just change the equation and then we know what the function pointer was. And this allows us to brute force ASLR without ever triggering a buffer overflow and without ever crashing the remote system. But we still need to brute force 28 bits of ASLR, which is still unfeasible, right? So there was a little trick we could use, which we aligned the out-of-bounds read so that it would only read 1 byte of unknown data, or 1 byte, the least significant byte of a function pointer. And if the rest of the data, say we want to read, there's a structure which stores a function pointer, and before the function pointer there's some known data or attacker controlled data, we can guess this, and we can just simply align the out-of-bounds read so that just 1 byte is unknown, which means we can use this oracle we just described, send 255 files to ClamAV, and then one of them would be guaranteed to yield in a virus being found, and from there we can just derive what this unknown byte was. And we can just simply repeat this process after we leak the first byte. We increase the alignment of the out-of-bounds read, and we do it again until we leak the full function pointer. So this is the ASLR bypass oracle. And just to summarize, we used the value of an out-of-bounds read to change the logic flow of the target to side channel the value that was read. So we observed the behavior, and just to put some pseudocode here, there's some sort of out-of-bounds trigger, and a value is retrieved. And then the application does something with the value. And as an external attacker, we may not be able to see what the value was. It may not be reflected back to us, but we can observe the behavior of the application. And if we're a bit lucky with the primitive, we can kind of derive what the value was, or at least estimate what the value was, depending on the path that is entered. For example, if an error was occurred, we can make some assumptions about the value, et cetera, et cetera. So, and by aligning the out-of-bounds read offset, we made the chance that we can influence the logic or narrow down the possibilities of the value a bit more likely. So in this case, we reduced the amount of requests an attacker would have to make to roughly 1,000. So yeah, let's put it all together. What we would do is, and in the interest of time, I'll have to stay very high level here. We leak ASLR with the aforementioned Oracle, and then we prepare a heap layout where we can overwrite a function pointer on the heap. And this triggers a buffer overflow, and then we do a standard ROP chain just to gain remote code execution. The function pointer we overwrote was called cbprocess in the RTF parser, and it's actually the same function pointer that we used to defeat ASLR that we read out of bounds. So let's get into a real-world case study in a scenario that is more realistic. So in this case, today we're going to target Zimbra. It's an open source enterprise email suite, and it comes with ClamAV installed. And every incoming and outgoing email is scanned, and no sandboxing is deployed. So Zimbra is commonly used by governments. For example, Valexity noticed some campaigns, mass exploitation of CVE 2022-27925 against government, military, and billion-dollar corporations. And recently, I read an article about Russian APT groups targeting NATO-aligned governments and to access military and diplomatic emails using a similar CVE. So we have a problem now, which is the Oracle relied on the fact that the attacker can get or see the value of, can get the result of the scan, so they will know if a virus was detected or not. But this wouldn't work in email, usually as an external attacker. And the reason for this is, say as an attacker, we send an email with containing a payload to the SMTP server. In this case, the SMTP server just tells us, okay, thank you for the email, I'm going to process this now. And it will then, in the back end, send the email to ClamAV first and then to Spam Assassin. But the attacker won't know, will never know if the email contained a virus or not. So how do we side channel the information now? So one thing I want you to notice or keep in mind is that in case of Zimbra, ClamAV, the virus was scanned first, and afterwards we did the spam checking. And we can do some very interesting behavior here, because ClamAV or the SMTP server will bail if ClamAV found a virus. And we'll see how this would lead to another Oracle in just a second. So the SMTP server, again, simply receives the email and responds to the attacker, and then queues the email. So there's also no timing-based Oracle that could somehow be possible, at least not reliably, not in the quantity and speed we need. So we need another side channel, and maybe we can exploit the fact that virus scanning comes before spam checking. So one part of spam checking is doing email spoofing validation. So whenever an attacker, or anyone for that matter, sends an email to an SMTP server, they can simply say, hey, I can be trusted example.com. But in order to validate this claim, the email server makes an SPF DNS request to the responsible DNS server. And the DNS server then responds with a list of IPs that are allowed to send emails on behalf of example.com. So we set this up with a collaborator suite where we can see if we just claim to be the following domain as the sender of the email, and the email didn't contain a virus, a DNS lookup is made, and that's how we know that the virus was processed, that the email was processed. So what we could do as an attacker is we would host a DNS server, and then we generate a unique subdomain per email, or a domain per email that is sent to the target instance. And when no virus is found, which means the ASLR Oracle did not succeed, spam checking is deployed and a DNS request is made. And once the DNS request comes in, we can verify, okay, this was apparently not the right offset. However, we can say after 60 seconds or 5 minutes, if no DNS request ever arrives, we can conclude, okay, for this particular offset, it seems that the email server bailed and did not make spam checks, which means we can side channel the fact that a virus was found, and then that's how we can side channel and find out that what the function pointer was. So now I've got a video for you So as a disclaimer, the video is speed up quite a bit. The real runtime is around, can I pause this? The real runtime is around 1.5 hours, can be even longer, just because it takes this long to set up DNS records and whatnot. So the video is quite speed up. And now we're seeing here, let me just try to pause this video. What we're seeing here is the first byte of the function pointer has been leaked after 32 tries. So we've leaked some of the function pointer already. And now we're just in the process of brute forcing the second byte. Oh, sorry. Okay, sorry about that. We'll just have to watch from the beginning. So this is the part that takes a while, and now the video is being sped up. And now we can just watch the counter go up and up, where it concludes which of the function pointer offsets it can reject. And we watch as the second byte has been leaked. Now the third byte is being brute forced, and now we're just brute forcing the last byte of ASLR. And we should now, in a second, see the location of libclamev.so and the function pointer, which have now been leaked. And now we're crafting the ROP chain, and hopefully we'll receive a reverse shell. And received it, and now we're the Simbra user and have achieved RCE. So just to summarize, just because the result of an out-of-bounds read is not reflected to an attacker or to you when you're writing an exploit, you can still try to side channel what the value was by observing how the application behaves based on this value. And a similar approach can be applied to scenarios where you target a load balance service, for example. So we use this, for example, when we know there are thousands of workers and we can leak ASLR in the first stage, but then the problem is, how do we trigger the second vulnerability with the same worker without just randomly crashing hundreds or thousands of workers? So in this case, you could, for example, use the logic, like using the pointer and constructing an oracle with some logic to try to only trigger a buffer overflow in case you got the right worker. We call it conditional corruption. So that's it. In case you have any questions. Thank you. Okay. Did you have a, okay. Okay. I guess in that case, also feel free to just approach me. Thank you very much.